So the central limit theorem, right, that describes the behavior the of the statistics. So in the one that we looked at, it was the distribution of the sample mean. But again, there are other statistics that we might come across. For example, S squared was the sample variance. So we could use the CLT for that and look at how that behaves. Okay. Another one that you're going to see coming up in the course is this idea of a sample proportion. And we represent that as p hat, and really all a sample proportion here is out of the total number of repetitions of experiment, or out of the total sample size that we might have, it counts what we call the number of successes. Okay, and so a success, I'm just going to say, here's defined a little weirdly, but it's just any event of interest. Okay, we actually computed this when we were looking at the rolling of a dice and getting, or a die and getting a 6, and 6 was considered a success. Okay, so if you want to think about it as the number of 6s out of the total number of rolls, that's what p hat is. Okay, we're going to use p hat when we're looking at chi-square distributions. Okay, but really, again, we use p hat as an unbiased estimator. Another vocab term, right? For the true population proportion P. Okay, so there we go. When we look at the sampling distribution for p hat, normal or the CLT still applies, and in fact we can actually say that the mean so the mean is going to be the population proportion, and the standard error, okay, or the standard deviation actually I should say standard deviation. The standard deviation for the normal distribution is given by this calculation, square root of p times 1 minus p all over n. Okay, that actually comes from the binomial distribution, but we'll worry about that another time. So anyway, there we have it, and in the same conditions still apply, so you still have to check in these scenarios, are your xi's IID, okay? The xi's would just be the events that you're looking at, and then are your mu and sigma finite. In this context, it's more just is p finite, but so are these values that we're working with, are those finite numbers? And then lastly, we would want to make sure that either n is sufficiently large or we are sampling from a normal distribution. Okay, so we should still verify the conditions for the CLT even in this context of proportions. Okay, since proportions are kind of new, let's do a couple examples together. Okay, so here I'll let you read the first example about the American Red Cross. Pause the video, resume it when you're ready. Okay, there's 3 numbers in here, and holy moly, I don't know what's what. This is where differentiating between statistics and parameters is crucial. Okay, so I see 45%. Okay, that 45% is actually our population parameter P. Okay, because it's describing all people and saying that 45% have blood type O. Okay, then the 1,000, that one I think is a little bit easier to pick out. That's just our sample size. Okay, and then this 42%, what is that? I don't know. Okay, but it's not p hat necessarily. Okay, but it is a crucial part of our probability statement. What we're looking at here in the question is, what is the probability that p hat is no more than, so less than or equal to, right, the 42%. And I'm using p hat here because I'm looking at out of the 1,000 medical records, I don't know the exact proportion I have. But what is the chance that the sample that I got, right, is less than 42% blood type O? Okay, so in that, I'm looking at a feature of the sample, and I want to say something about the sample. Okay, so now to calculate this is where things are going to get a little interesting. Okay, because we have to use this distribution, right, to calculate it. We're going to use the normal distribution. So I would normally start off with, one, or in this case, since I'm going to the left, norm.dist. my value of interest, 0.42, the mean, which is the population proportion, 0.45, and then now I need the standard deviation. This is one where I would recommend calculating it off to the side. Okay, maybe I shouldn't label it sigma. I'll just say standard deviation. So this is going to be square root of 0.45 times 1 minus 0.45 all over square root of 1,000. Okay, and I'm going to calculate that. And I got a very small, long number, and honestly, you should include as many digits as you possibly can in these intermediate stages because it's going to matter. So that's what I got. Okay, so then I'm going to put that number in there and then do true in Excel. Okay, and then I'm going to get a number. Okay, so let's go to Excel and calculate this out. So in Excel, I'm going to do equals 1 minus, or sorry, actually not 1 minus in this case, norm.dist, 0.42, 0.45, and then 0.0157, 32133, true, and I got about 2%. Okay, 2.8%. All right, so then I can go back and report that. Okay, so about 2.82% of the individuals in our samples, or sorry, 2.8% of our samples would contain no more than 42% of the individuals with blood type O. That's how we interpret it, okay? 2.8% of the samples we receive would contain no more than 42% of individuals with blood type O. Okay. Next example. Okay. So I'll let you again pause the video, read the context. Okay. And so then if we look at p hat, right, and we're looking for the mean and standard deviation according to the central limit theorem, we are going to assume it applies. Technically it doesn't because we don't have normal and we don't have a sample size of 27. But we can say just for fun, okay, just for fun, that P is approximately normally distributed with mean of 0.25 and standard deviation of square root 0.25 times 0.75, 1 minus 0.25, all over sample size of 27. Okay? And surely you can simplify this, and if you do, that this is the same as 0.25 comma 0.083 bar. Okay, meaning it repeats. Okay, so then what is the probability that the sample proportion is at least, so probability that the sample proportion is at least 33%. Okay, so then this is where, again, since it follows a normal distribution, we can do 1 minus norm.dist, 0.33, 0.25, and 0.0833333, a few more of them if you want, and then true. Okay, and when you do this on Excel, you get about 16 or 0.1685, okay, or 16.85% of the samples, okay, would have a proportion of males that is at least 25%. Okay? 25% male. Okay, 25% of the incoming class would okay, there's a 16.85% chance that an SRS of size 27 from the class that enters UMR would be approximately 25% female, or male, 25% male. Okay, that's how we can interpret this number. One word of warning as we close this video. With the sampling distributions for p hat, okay, if you get a p hat that is close to 0 or 1, that's going to throw your calculations off a lot, okay? So as a remedy for that, you should actually increase your sample size so that your p hat actually gets a little bit smaller. But for us here in our class, you're not going to see any examples like that. You're just going, just in practice, if you ever come across that situation, you would need to increase your sample size. Okay, so chapter 13, lots of theory, lots of interesting applications, and probably lots of questions. We'll be sure to talk through them when we see each other next.